Mhm. Sorry. Um, so we learned that the majority of radionuclide which are used for nuclear medicine application are metals. And this opens a broad range of different labels. So majority of elements are metals, and radiometal technology creates a precondition for selection of an optimal label. The problem is that we need somehow attach a radiometal to tumor targeting part. So, and tumor targeting part in majority of cases is organic molecules. Nowadays, it will most likely be protein or peptide. But the problem is that binding of metal to organic molecules is very weak. One can, of course, use thallium or tin compounds, but they are very unstable. Actually, metals are used very often as a living group. So we need to find a substitution for direct covalent attachment of radiometals to organic molecules. To get an understanding for such process, we need to consider status of metal ions in solution. Well, when I started to learn chemistry in school, we learned about theory of electrolytic dissociation of ionic compounds, proposed by Svante Arrhenius, chemist from Uppsala University. And what we learned that the crystalline lattice of ionic compounds got destroyed, and ions, cations or anions are distributed more or less randomly throughout the solution volume. And feeling is that they're distributed pretty chaotic. Some metal cations, some anions around, probably interaction with water. Well, this is the truth only partially. In fact, the metals very often start to interact with counter ions and with solvent with water molecule in solution. Of course, there might be sort of electrostatic interaction between positively charged atoms and negatively charged counter ions. So the water molecules have a dipole character with negative charge on the oxygen part. So that start to orient the atoms around. It start to coordinate them. And such complexes, coordination compounds, might be very unstable, very transient, just dissociating spontaneously every second and every second reassembling, or they might be pretty stable. In some cases, they start to form dative or donor-acceptor bond with the metal, which definitely stabilize the whole construct and you could sometimes even crystallize the whole structure. Well, classical example are sulfates of copper or iron. So one says that it is formed an coordination complex compound which typically consists of central atom which coordinates around a ligand. So in this example, we have square bipyramid and with anions on equatorial plane, let's say, and water dipoles located on the vertices of pyramid. This is only half of the story because counter ions or ligands could also form the interaction with other surrounding ions. So, for example, anion could interact with positive part of water dipole, and the water dipole could interact with anions and so on. So we actually having typically an ionic compound in solution, we organize this solution in strong way, forming by complexes, and those complexes are characterized by stability constant, which is ratio of concentration of a complex and concentration, product of concentration of the ligands and central atom. So now let's imagine a ligand which can occupy more than one position in coordination sphere. Well, this is examples of quite commonly used in laboratory ligands, such as D-ethylene 3-amine pentaacetic acid or DTPA, or ethylene diamine tetraacetic acid. They could interact with the metals in many ways. It might be simple electrostatic interaction between negatively charged oxygen and positively charged metal. Nitrogen atoms have typically unshared electron pair which they could donate to empty vacant orbital of transitional metal and accordingly form a dative bond. So such multi-functional, or one say ligands could called chelators. Their capacity to occupy certain position in inner sphere called denticity, as dent, the number of teeth on this chelator. For example, DTPA is octadentate because it contains 8 potential donors of electron, 3 nitrogen with the unpaired unshared electron pairs, and 5 carboxy group, which carry negative oxygen atom. EDTA is accordingly 6 hexadentate because it can occupy 6 positions in the coordination sphere. Well, question is Okay, they can. Why they should? To understand this, we went to very basic science in every natural research area, thermodynamics. And if you remember school or university courses, you should remember that any reaction is governed by change of Gibbs energy or free energy in the system, which is composed by change of enthalpy and product of temperature and entropy. So overall, any system tries to get a position in energy where the total energy is a minimum and disorder is maximum. I used to tell about my desk as perfect thermodynamic system where mess happens spontaneously. So overall, the reaction happens if the system uh, reduces the energy and increases disorder. So let's see what happens if we substitute multiple monodentate ligands in the coordination sphere of the metal. Here we could see that we have 7 atoms which are pretty organized, which could move only as a whole, and there is very little freedom of the component. So overall system consisting from a complex of metal with transitional atom and ligands and chelator is pretty much organized. So only a few particles can move independently. Let's see what happens if we form a complex where all the positions in coordination sphere are occupied by um, single chelator. Now we have 7 particles which are capable of independent movement. So system got pretty disorganized. So that means that we increasing entropy quite a lot. So formation of such complexes between a metal and chelator, the one use the term chelate for such complex, is driven by entropy or increasing of entropy and substitution of multiple monodentate ligands by single polydentate. So depending on the composition of donor group, of geometry of the chelator, such complex might be quite stable thermodynamically. And this solves the problem of attachment of metal to organic system because the backbone of such chelator is typically organic, and we know pretty well how we can attach one organic molecule to another, even such complex as protein and peptide. It has to be noted that we have to have so-called bifunctional molecule, which contains two parts, each exercising own function. First, it's a chelating part, which complex the metal and holds it tightly, and then the part linker, which should couple this whole complex to tumor thickening agent. Well, in this example, we could see isothiocyanate derivatives, benzyl isothiocyanate derivatives of DTPA, where DTPA part is responsible for chelation, for example, of indium, some cases lutetium, and it contains isothiocyanate group, and which capable to form thiourea bonds with amino group, for example, terminal amino group of protein or peptide, or omega amino group of lysine. So now we have a tool which enables us to conjugate radiometal to tumor targeting peptide and protein. There is one important aspect which we have to keep always in mind. The chelator formation is always reversible. When we have covalent bond, well, when we label, for example, small molecules with carbon 11 or carbon 14 to this end, or when we introducing radiohalogen, whatever, fluorine 18 or heavy halogen, it forms a stable covalent bond. Covalent bond does not dissociate spontaneously. You generally in vivo need some enzymatic system which force it to dissociate from organics. Metals are always reversible. To a certain extent, it happens constantly dissociation, though equilibrium in good chelators are shifted to complex formation, not dissociation. And that would be fine, but we have in vivo plenty of proteins which also possess metal chelating properties. For example, transferrin is a blood protein which has a function of transfer of iron from one side to another, and it unspecifically chelates majority of three-valent metals, some of them very strong, for example, gallium. Ceruloplasmin, this protein mainly is responsible for copper transfer because copper is essential element. Even albumin, the most abundant protein in the blood, also possess the metal chelating properties. And they are constantly challenging the chelator in vivo. So as soon as metal is dissociated from chelator, it can be taken up by such chelating protein and transfer in a rod place, or fix it in the blood where it would circulate for a long time creating unnecessarily background and reducing contrast of the image. So traditionally, stability is described by equilibrium dissociation constant, which is determined by ratio of product of concentration of metal and chelate. And for medical application, it's very much apparent that KD or dissociation constant for chelator should be much higher than dissociation constant for complexes with chelating protein. It's no wonder because in the end, the injected radiopharmaceuticals would be utterly diluted in the blood, while blood proteins are everywhere and challenging. Usually to characterize the stability, one uses minus logarithm of KD. And let's say K minus KD logarithm of 20 is a minimorum requirement for stability of such complexes. Good chelator, for example, NOTA in combination 1 gallium 60, 68 or 67 has minus logarithm KD of 30 orders of magnitude higher stability of the complex. Still, we have a loss of metals every time. It might be case when our targeting protein resides for a long time in blood, as a case for antibody, or it might happen that complex is finding its place in tumor where it is internalized or in excretory organs where it is digested by proteolytic enzymes, and there might be loss of metal from the chelate. To overcome this problem, a concept of macrocyclic chelator has been proposed. As we have discussed already, the chelate formation is entropy driven, and we gaining Gibbs energy by letting monovalent ligand just diffuse freely by substitution them by single chelate. But it's not the whole story. Typically, chelator consists of many organic parts which are relatively loosely connected to each other. Apparently, there might be rotational movement, for example, around nitrogen atoms. It might be vibrational movement, and so on. And this is, of course, related to every part of such complex. So there is still certain freedom of movement inside the chelate. And when we arrange it around a metal atom, such freedom of movement is lost. So we still decreasing entropy, though not to the same extent as just the free movement of whole particles. So we losing our chaos in this case. So was an idea around 40 years ago proposed that pre-organize chelators, create so-called macro cyclic effect where part of chelators are arranged in the right position in advance. And this would prevent loss of chaos. Here are a few examples of such a macrocyclic chelator. Here is a chelator called theta, and you can see that nitrogen atoms are placed inside a pretty rigid structure which can surround in the central cavity of the metal, and then it's only carboxy groups would be restricted in their movement. So formally you gaining the chaos and you can form more stable complexes. Here are two other examples of macrocyclic chelators. One is daughter, also having 4 nitrogen atom and 4 carboxy group, though the system of organization a bit different, and not a chelator, so-called 3 other chelator, which contains 3 nitrogen atom pre-organized and then having 3 carboxy group. What is interesting that release of metal from complexes with macrocyclic chelator indeed is lower than from complexes with acyclic chelator. Bingo. Well, not whole truth here, because gain, as turned out, was not by thermodynamics, not by stability of complex, but rather by inertness of complex, slow dissociation from such a complex. Well, no matter, we hold our radiometals in complexes with macrocyclic chelators quite firmly. And this is important because if radiometal is dissociated from complex, it could create a lot of trouble. Well, if it's excreted, it's only half of the issue. It can be taken up by bones in many cases. It can be taken up with metal storage system, and in liver we have several metal storage proteins such as ferritin or ceruloplasmin, or it can bind to metal transport protein and stay for the long time. So the use of macrocyclic chelator in many ways simplify the further imaging and permit more contrast imaging. So apparently high stability is probably wrong term. Low release of metal is apparent advantage of macrocyclic chelator. It has, however, certain disadvantages. First of all, it's rather slow incorporation of metal in such complexes. Generally speaking, one could say that the complex formation happens in two stages. First one is rapid, it's off cage. Complex formation when metal is loosely bound by electrostatic interaction with carboxy group. And this is a quick. But then the carboxy group have to drag in central cavity. And this requires also some rearrangement of central cavity, so it's energy-driven process and it's slow. So to speed up this process, we often need to warm reaction mixture of targeting protein conjugated with a macrocyclic chelator and our radiometal. So some proteins, peptides generally withstand warming easily. Some proteins, like scaffold proteins, withstand warming easily. But if you take, for example, an antibody, the warming might be associated with the risk of denaturing. Generally, no one dares to warm an antibody solution to higher than 40, 42 degrees centigrade. So this is one of limitations of macrocyclic chelator. Another issue is the ratio between ionic radius of a metal and central cavity of such a macrocyclic chelator. So you have to have an optimal distance between radiometal ion and nitrogens which act as electron donor. If the distance is non-optimal, so that you start to disturb the angles in the complex, so you're again stealing energy. So for example, for gallium, the best chelator is nota. For copper, best chelator is theta, and so on. So in ideal world, you need to have different chelators for different metals. It's difficult to create universal targeting molecule. Still, there is a sort of magic bullet here. It's a chelator called DOTA. It's tetraazo chelator containing 4 nitrogen, and it proved to be reasonably stable in complexes with indium and gallium for imaging, SPECT and PET, for therapeutic high and low energy beta emitters, and with a number quite heavy atoms like lead or bismuth or even actinium and thorium, which can be used for alpha particle mediated therapy. And thorium is quite big ion. It has to be noticed, though, that one has to warm it nearly to 100 degrees centigrade to squeeze thorium in the central cavity of the dot chelator. Of course, what I have shown you before, it is just a monofunctional chelator which has to be functionalized uh, for coupling to tumor targeting molecules. Very commonly used variant is succinimidyl ester of DOTA, where one arm is coupled to succinimide. So in solution in alkaline condition, amino group attack this carbon, and it leads to formation of amide bond, which is stable between the chelating part and amino group on targeting protein. We always have at least one amino group at N-terminus, but also you have lysines, or for peptide synthesis, you can use orthogonal protection scheme where you essentially could place this chelator in any position. So such chelator is commercially available. This is an advantage. You need them to synthesize every time yourself. Coupling is quick. It can be used during peptide synthesis, and peptides are one of the most promising classes of targeting probe for nuclear imaging and therapy of malignant tumors, and not only that. Disadvantage of such chelator is that one of carboxylic arm is used for coupling. So that means that while initially this DOTA is octadentate, after using one of arm, it starts to be heptadentate. Not always good. Many lanthanides are octa-coordinated, and that means that one of position coordination sphere is vacant, not occupied by chelator, and that might result in challenge by other chelating agents. Another problem is that this labeling is not site-specific. Typically, there are plenty of lysines on the surface of any protein, and you never know where these chelators will be coupled. It's also not very easy to control this coupling because you have two competing processes. One is coupling to amino group, and second is simple hydrolysis, which results in formation just of free DOTA, which is, well, non-reactive. There is another type of bifunctional derivative of DOTA, it's so-called backbone modifier. So in this case, benzyl isothiocyanate group is conjugated directly to backbone of the DOTA chelator. So in this case, you have all four carboxy group available for chelation of a metal in addition to four amino group. So you have true octadentate chelator, and isothiocyanate is capable of forming um, thiourea bond with amino group, and that offers apparent advantages. So first of all carboxylic arms are used for coupling of metal, not for conjugation to targeting moiety, and conjugation in aqueous media is very well controlled. In my experience, you have coupling efficiency in alkaline solution of about 90%. You take 10% excess of isothiocyanate and you have, on the average, 1 chelator per 1 protein group. And that was measured by mass spectroscopy. Well, nothing is of course perfect, and major limitation is, for example, the thiourea bond is labile in acidic conditions, not moderately acidic condition, which we use for labeling, but in strong acidic conditions, for example, when we use for cleavage of synthetic peptide from resin in peptide synthesis, thiourea bond will not survive. So it's more suitable for coupling in solution rather than coupling during peptide synthesis. And again, there is the same disadvantage as succinimidyl ester is the no specificity. Well, once upon a time, it was a big issue for us because we wanted to label affibody molecules with DOTA and do it in site-specific manner. In this case, we use the fact that affibody scaffold is cysteine-free. There is no single cysteine. So if we introduce a cysteine by gene engineering, there will be only one SH group in the whole protein. So that creates a precondition for site-specific labeling. So with this tool in hand, I managed to persuade guys from Macrocyclics, a company which produces macrocyclic chelator for commercial delivery, and they made a variant where the one of carboxylic arm is conjugated to maleimide group. And maleimide group is capable to undergo so-called Michael addition with SH group and form covalent bond which is reasonably stable. Not ideal, but not as strong as to the amide bond, but it's stable enough. So that give us very well controlled conjugation in aqueous media. So in my hands, coupling efficiency is roughly 70%. And if you take typically excess of 3 such chelator over protein, you have 100% coupling efficacy. And of course, then you could purify easily non-conjugated chelators, and can be used for scaffold proteins. It can be used for labeling of prime fragments of antibodies, for example, which typically contain free SH group in site-specific manner, which is good advantage. So your structure of your targeting protein is always the same, which means that biodistribution is always the same. Well, problem is, of course, the control over reoxidation of tile, because normally, slowly but surely, SH group will interact with each other, forming disulfide bond. So typically you have to reduce disulfide bonds before coupling, and then take measure that you take away whole batch of reducing agent and keep in probably slightly acidic condition, which is favorable for keeping the disulfide bond from the dimerization. Well, as I mentioned, that disadvantage of macrocyclic chelator is warming, and far not every protein can be warmed without denaturing. The solution came in form of so-called semi-rigid acyclic chelator. Here are two examples of semi-rigid DTPA derivatives. They both contain the benzyl isothiocyanate moiety for conjugation to amino group of, for example, antibody, but they have also some organic constituents. For example, in chelator tioxetan, it's a simple methyl group which is attached to the shoulder of BTPA. Surprisingly, that reduces freedom of rotation of this chelator and stabilizes complex pretty well. So it's now that complex of yttrium, yttrium 90 with DTPA is not sufficiently stable. And yttrium is used for therapy, and this is high energy beta. So if you're losing control over yttrium, it's trouble. But simple SH group in this position stabilizes the complex very, very good. And Zevalin, therapeutic antibody for treatment of leukemia has exactly this chelator, and this antibody is used for more than a decade for treatment of hematologic malignancies. My personal favorite is CHX prime prime A prime prime DTPA. Here is not a single methyl group, but cyclohexane attached to this molecule. So this molecule has been developed by Otto Ganso and Martin Breisbill. It's a tricky that there are totally 4 different stereoisomers, and only one of those isomers is really stable. So I think Martin Breisbill was got a co-author for 300 paper just by supplying this chelator to different researchers who were willing to make stable conjugation. Now it's commercially available to a reasonable price from a company called Macrocyclics, and I evaluated it once upon a time with cyprium, with lutetium, and came to conclusion that with indium, so that there is no difference between stability of CHX A prime prime, DTPA, and DOTA. But advantage is that it can be labeled at room temperature within quite reasonable time. So for labeling of antibodies or other constructs for therapy, that is solution. Actually, Martin did once upon a time for me this variant with maleimide derivative, and we use it for site-specific conjugation to antibody molecules. It works as well for this purpose. So acyclic chelators are chelators of choice when you need to label sensitive proteins, such as antibodies. So they offer high stability, rapid labeling kinetics, and they are commercially available, which simplifies your life pretty much. So, what one has to remember when working with chelators, generally speaking, chelators are not selective to nuclides or elements. One exception is some phosphotriazo chelators, which might be selective to gallium, but generally they take all transitional metals. And here are examples of some common metal impurities which can kill any chelator just by competing with radiometal for placing chelators. Chromium, iron, cobalt, nickel, zinc, lead. If you don't take away from your solution, you are in trouble. Problem is that if you take even very clean acids for your buffer, you generally exceed by a few orders of magnitude concentration of metals. Especially dangerous is iron. We still live in an iron age, and every particle of dust which flowing in your lab might contain rust, and a few dust particles could contaminate your solution irreversibly. What we do for that, we use an ion exchange resin called Chelex. It's immunodiacetic acid immobilized on polystyrene divinyl benzene backbone, and which is very, very avid to all transitional metals. So we store our buffers over the Chelex, and we in this way prevent from metal contamination our solution. Surprisingly, standard polypropylene Eppendorf tubes are pretty metal free, but many researchers recommend to use acid wash of all plasticware in the lab before working with radiometal. So as I say, that you have to be paranoid about metal contamination if you work with radiometals. This is first part of today's lecture, and we might have a short break, and probably you could ask your questions. Я принимаю вопросы по-русски, если что-то непонятно. Ладно? Вопросы есть?
Да.
Угу.
Вот поясните, пожалуйста, не успела уловить суть покрытия материала полипропилена с пробирок. Как он влияет на связывание с металлами, или как это избежать?
Еще раз извините. Я не очень хорошо, к сожалению, вас слышу.
Сейчас попробую. Сейчас слышно лучше, да?
Ну, чуть получше, да.
Так. Вот вы поясняли, что помимо того, что нужно очищать все растворы, готовить, ну, и с хеликсом очищать, полипропилен пробирок, вот как он влияет? Я просто не уловила немножко мысли. Как
Нет, я насчет того, что стандартные эппендорфы полипропиленовые достаточно чистые от металлов. То есть, ну, скажем, в Nature Protocols есть статьи, там, Кэролайн Андерсон, которые вообще советуют все сверхчистой солянкой мыть, чтобы избежать загрязнений.
То есть этого не требуется, да?
Ну, как правило, нам не нужно таких удельных активностей, чтобы это нам здорово помешало. То есть, что может и точно мешает, это буферы. Вот. При этом, ну, мы говорим, то есть, вот химиотехнеция я просто вынес в отдельную историю, потому что там химия здорово отличается от всего остального. То есть то, о чем я говорю сейчас, это преимущественно трехвалентные или двухвалентные переходные металлы, вот, которые реально боятся металлической грязи. Но я в свое время посчитал, пытались метить фактор роста эпидермиса галлием. С доту приконъюгировали, использовали сверхчистые реактивы для приготовления буферов. Значит, 4 девятки, так, ничего, чистота. Значит, я имею в виду 4 девятки после запятой. Значит, не получилось ничего. Попробовали, я тупо вот на пальцах посчитал соотношение железа согласно паспорту и количество галлия. Выяснилось, что у нас железо в этом сверхчистом реагенте на 4 порядка больше, чем мы имеем галлия в нашем растворе. Вот, поэтому, то есть, лучше не хранить буферы в стеклянной посуде, потому что стекло выщелачивает металлы, ну, вернее, кислоты выщелачивают металлы из стекла, при этом, значит, идет диффузия из толщи стекла к поверхности. Пластик всегда вернее, чем стекло. И самое лучшее – это хранить их над челексом. И вот в последний момент перед мечением фильтровать, чтобы не ухватить ненароком частицу челекса. Еще?
Ясно.
Ладно. Значит, это были химические аспекты. Now we're switching to biological aspects of radiometal labeling. And this is very important when we're talking about proteins and peptides. Generally speaking, the use of radiometal improves appreciably intracellular retention of radionuclides. Here we coming back to this cartoon, which is very essential for us, and we will come back to it several times during our course, and that concerns permeability of cellular membrane. So the cellular membrane is phospholipid bilayer, which has hydrophilic head and hydrophobic core. And hydrophobic molecules could relatively easily diffuse through cellular membrane. They just come to it, dissolve in hydrophobic core, and could redissolve on the other side of the membrane. And they will do this if you have a concentration gradient, because the concentration gradient is always driving force for diffusion. Carbon dioxide, benzene, oxygen are freely diffusing. And it also making lipophilic enough or hydrophobic enough molecules is a way to transport radiopharmaceuticals through, for example, blood-brain barrier. Even if molecule is small but uncharged polar, so it's still capable to penetrate through cellular membrane. But larger molecules, like glucose, for example, or any sugar, If they are polar, which is a case in the case of glucose, they cannot diffuse through membrane easily. So you need a transporter for sugars to get inside the cells. And ions definitely could not penetrate. So the whole paradigm of cell biology is based on impermeability of cellular membrane to charged ions. Now, what happens when our targeting protein binds to a tumor cell? Typically, if you have, for example, an antibody which binds to tumor surface antigen bivalently, or you have a ligand, agonistic ligand to a receptor, binding to cell surface antigens, so cell surface target triggers internalization. It's so-called cluster-independent mechanism, where binding of our targeting molecule, for example, and cross-linking, results in conformational changes of intracellular part of the molecule of the target. It recruits intracellular protein called clustering, which just pinch off part of the membrane, transfer it to endosomal compartment, to lysosomal compartment, where happens acidification, activation of proteolytic enzymes, and generally speaking, any protein which is ending up in lysosomal compartment got degraded to single amino acids, or, well, around it might be your radiocatabolites. Then the fate of the label might be very much different depending on physicochemical nature of radiocatabolites. So in case of metal chelators are always very polar, nearly always, charged very often. So they cannot penetrate cellular membrane, so they got trapped inside the cell. Then it happens slow process, externalization, which, well, sooner or later, of course, they will be excreted from the cell, but it would be rather later than sooner. Opposite situation is when we have lipophilic radiometabolites. And this is often the case for radiohalogen label. That happens with iodine, with bromine, and in the majority of cases with fluorine label. Whatever you use for fluorination. One exemption is alpha chemistry and chelator. So pretty lipophilic catabolites which can diffuse through the cell and just get away from cancer cell. I would stress that internalization takes place always. The difference is the rate. So if it's receptor-mediated internalization or cross-link internalization, it might happen within minutes. It might be that the forced internalization doesn't take place. It's still happens which with much slower rate because cell used to clean its surface. So there are certain receptors expressed on the surface of the cell, and so they used like chemical antennas. And very often the expression level depends on physiological condition of the cell. So it changes with the time accordingly. Cell need to clean. So it's approximately 30% of cellular membrane a day goes the same way. So through endosome, lysosomes, and unnecessary receptors are taken away. But that process is always there. And we can play with it. I will show you how to do it. Well, but generally speaking, lipophilic catabolites are leaky. And there are definitions which now commonly used in English literature. So the labels which remain trapping intracellularly after internalization called residualizing. I have discussed with my colleagues in Russia about how to translate residualizing. So there is no standard word. So I propose to use the term удерживаемые as residualizing. And they are typically product of bulky, polar, and often charged metal chelates. Here is example from one of our pretty old work when we labeled epidermal growth factor with different labels. So epidermal growth factor receptor is overexpressed in many carcinoma, for example, in head and neck tumors, and lung carcinoma, and so on. It is a target for antibody cetuximab. So we try to find an optimal label to its natural ligand, epidermal growth factor, which is short robust protein with molecular mass of about 6 kilodaltons. So if we label epidermal growth factor with iodine, let it bind to receptor on cell surface on ice to prevent internalization, and then warm it up to 37, where internalization takes place. Release of activity is very, very rapid. It's not a dissociation. It's taken up, degraded, and catabolites are leaking. It's around 1 hour half-life. Then everything is gone. When we used the different derivatives of DTP, there was a striking difference in retention activity. And this is effect of a residualizing plate. So that makes sense. And in the case of rapid internalization, you have to use residualizing plate. Good example, somatostatin analogs like octreoscan, like TOP, tyrosine octreoscan. It's useless to label them with iodine. It will be gone because those variants are agonists which are rapidly internalized. We did estimation for antibody, for example, anti-HER2 antibody trastuzumab. So after iodination in the same assay, we have 25-30% of cell-associated activity compared to time point 0. If we have Radiometal, it was 80% or even more. So that is the only possible way. Still, retention of residualizing label is high also in normal tissues, which if there is an internalization. And one of healthy tissue where proteins are often internalized is a kidney parenchyma. So generally, kidney work as dialysis apparatus inside, so blood goes through glomeruli where you have membrane which act more or less of dialytic dialysis membrane with cutoff of around 60 kilodalton, and everything which is smaller than that goes to primary urine. Still, primary urine might contain quite a lot of different proteins and peptides. It includes the albumin, which should stay away, but some breakthrough is there, a lot of signaling substances. And it's too wasteful to let it go to urine. So there is a machinery inside glomeruli which take care about proteins. So so-called brush border surface where several classes, megalin, tubulin, some other, taken up from primary urine proteins, peptides, transferred to lysosomes, endosome, lysosome, where they are degraded. And metabolites can come either back to lumen of proximal tubule or return to blood. So apparently, if you have non-residualizing label, it will leave, and residualizing label would be retained inside the proximal tubule in a kidney. Here is one good example. This is first generation of affibody molecules we worked with. It's a scaffold protein with a molecular weight of approximately 6 kilodalton, between 6 and 7. And we label these affibody molecules with either indium using benzyl DTP or using para-iodobenzoate with iodine. Uptake in tumor was approximately the same, a little bit better for Radiometal label, but striking difference was in kidney. So kidney were really shiny in the case of Radiometals. So essentially, 4 hours after injection of this affibody, we had approximately 10–15% of injected dose per gram of kidney, per gram of tumor, around couple of percent of activity in liver, but rest was taken up by kidney and stayed there for days. When we use non-residualizing label, it was taken up to the same extent by kidney, but 4 or 6 hours after injection, for example, it was gone nearly completely. So you can play with the label, and we did this because we measured internalization rate in vitro, and we knew that internalization rate of antibody molecules is slow by cancer cells. So it was slow by cancer cells. Residualizing property were not essential, but it's rapid in kidney. And here we could get positive effect of using non-residualizing clay. Also, the chemical, of course, nature of radiometabolite plays role, and it looks like also positioning. Here is a graph demonstrating retention of antibody molecules in kidney. Radiometal, 250% of injected dose per gram. I know that it might sound shocking, but it's per gram is important. So in mice, kidney have weight roughly between 200 to 400 milligrams. So per gram, if your uptake is 70% and kidney mass is 300, so you would have around over 200% of injected dose per gram. And it was retained up to 3 days, well, with quite slow release. When we use label para-iodobenzate, it was much quicker, and when we use hydroxyphenylethyl it was even quicker. So this creates a precondition to molecular design. You need to understand the behavior of your targeting molecule and adjust the label to meet major requirement, high uptake in site of interest and low uptake or low retention in sites where the activity is undesirable. So talking about residualizing radiometal, we could tell that renal reabsorption depends on targeting protein. Some of proteins can go through kidney rather without reabsorption. For example, nanobody is a single domain antibody, had a high reabsorption when there was hexahistidine tag for purification, but cleavage of hexahistidine tag result is much lower reabsorption in kidney. Unfortunately, all scaffold proteins we work with, it's antibody molecules, it's the DARPins, it's ADAPs, they have high reabsorption. And we try to make different, actually we tested everything which has been described in the literature. We could not reduce the absorption meaningfully. So we use other approaches to minimize that. So reabsorption is dependent on the targeting protein or peptide. Retention depends on labeling chemistry, renal retention. So, and apparently for each protein, this must be evaluated to select an optimal labeling chemistry. Especially when we're talking about the therapeutic application. For diagnostics, it's not so important because the metastases in kidney are not important, and if you are not targeting renal cell carcinoma, it doesn't matter. But for therapy, of course, if you have 15-fold higher accumulation activity in kidney comparing to tumor, you will burn kidney before you manage to disturb tumor. So summarizing today's lecture. So radiometals can be bound to targeting protein and peptides using chelators. For different metals, we need to have a different chelator. Even the most versatile chelator, DOTA, is not perfect. For example, it's a bad chelator for copper isotope. Metal-free conditions are critical for successful labeling with radiometals. You have to be paranoid about metal if you want to work successfully. The use of radiometals improve intracellular radioactivity retention of internalizing targeting protein, but renal retention of radionuclide is also dependent on visualizing properties. And labeling chemistry may influence retention of and excretion of targeting peptide and radiocatabolites. And that means that careful optimization of labeling method might make a difference between success and failure in development of radionuclide agent for therapy or for imaging. Так. Ну, здесь, наверное, мы останавливаемся. Какие-нибудь вопросы есть? Алло.
Посмотрим, может, кто-нибудь сейчас задаст вопросы.
Да, я очень доступно объясняю все.
Ну, по второй части уже более понятно.
Ну, в общем, мы работаем с металлами много. Что касается технеции, то, в общем-то, это тоже металл. Он со своими вензелями, как говорится, но тем не менее. То есть, в общем-то, вот эти вот базовые понятия, они остаются теми же самыми. То есть, если мы говорим о развитии химии в Томске на данный момент, то это прежде всего химия технеции. Дешев, доступен, вот он просто рутинно используется. А это радиометалл Следующий, на что мы надеемся, ну не просто надеемся, мы работаем над этим, это, скорее всего, будет радионуклидная терапия с лютецией, а это радиометал. Ну и, наверное, даст Бог, мы сможем работать также с йодом 123. Ну, вот, мы начали это обсуждать, и я надеюсь, Мария уже там начала смотреть на химию или...
Да, да, мы вот сегодня с Екатериной Подрезовой обсуждали как раз статьи, которые выслали. Реактивы все есть. Ну, не метилбутил, бутил только.
Ну, мне Мехман об этом говорил, ну, пусть будет бутил, это лучше, чем ничего.
Да, и Катя начнет с этой недели уже пробовать синтез ставить.
Ух ты, ну, молодцы.
Ну, реактивы есть, повезло.
Ну, да. Угу. Ну, хорошо. Так, то есть больше вопросов нету, да? Так, я не уверен, что я до этого встречался лично с Екатериной Подрезовой, по-моему, нет.
Ну, она здесь, Катя. Катя.
Вот, так что рад с вами встретиться и надеюсь, будем работать дальше. Так, ну ладно, тогда вопросов, если точно больше нету, то я бы попросил, так, Екатерину Безверхнюю, а вот, да, Мария Третьякова здесь. Тогда всем спасибо за участие. Значит, текст я, вернее, рекординг я останавливаю, и даст Бог оно будет. Я